Hello everyone, this is the third video I've uploaded I'm going to upload today, and it's going to be on question A3 of the 2013 semifinal USA Physics Olympiad exam. So this problem, it tests on relativity, some simple, very simple relativity. What it deals with is time, proper time, and the Lorentz factor. Alright, so in this problem, a beam of muons, travel in a circular orbit, and so it gives a mass of these muons, the charge, and their half-life. Part A of this question asks for what the magnetic field is. So, we do know that according to circular motion, and according to charges moving in a magnetic field, that the force is mv squared of r, and the force of the B field would have to equal that to maintain this circular motion, equals QVB. And from the simple setup, let's just quickly solve for B. B we get is equal to mv over qr. Okay, so now we have to account for relativity, and even though it is traveling much less than the speed of light, the second question does ask about if it was traveling a lot faster. So basically, what happens is when something is moving very fast, let's say you were the charged particle. The frame of reference was you standing on, let's say you could stand on the charged particle. So if it was to move one complete circle, right? From your perspective, if you look at your watch, but if you were traveling very fast, the Lorentz factor, which is derived from, I believe, like a train setup or something like that, an observer outside who is observing your motion would record a time. What is that time they record? It would be t times. It would be equal to gamma times t. And gamma is equal to 1 over the square root of 1 minus v squared all over c squared. No, v squared over c squared. So that would be equal to t over the square root of 1 minus v squared over c squared. Alright, so now, t naught, proper time. So now let me explain what proper time is. Proper time is the time measured in an inertial reference frame between two events that occur at the same position in space in your reference frame. So if I was standing here, I started here, I would record the event at 0, 0, and I go in a complete circle, and I would end at 0, 0. So that would be proper time. But then you might ask, if I was over here, let's say an observer who is watching this muon move in circular motion, this is a horrible circle, doesn't it also start and end at the same position in my frame of reference as well? Well, see, the difference here is that in my frame of reference here, wherever I am, I would always be 0, 0, because I would be following this muon. But here, when it's over here, this would not be the same. It would not be the same position as where it started, right? This event starts from here, and it ends here. And these are not the same positions in the outside observer's frame of reference. Therefore, this particle, according to gamma t naught, where gamma's greater than, or I'm not sure about equal to, but yeah, it's basically greater than 1. It would take longer. So therefore, if I sum up all these tiny segments, it would overall take a longer orbit time in my frame of reference. So that is the precise reason why we use gamma t, and the precise reason why, from this observer's point of view, this is not proper time from our observations and looking at our watch. Alright, So now that we have that established, what proper time is. Oh shoot. The undo only goes so far, so we'll just have to scribble this out real quick. Okay, yeah, this is very tedious. One sec. Alright, so this Lorentz factor, this gamma, applies to our problem, and they do tell us about it. They say that the momentum is really gamma mv. That is gamma mv. And this is called, for your information, time dilation. So, we can see that there's an mv over here. That is the momentum. So, let's rewrite this more accurately as gamma mv, which would account for a particle moving super fast. See, since gamma is equal to 1 over square root of 1 minus v squared over c squared, where v is our velocity and c is the speed of light. If we were moving very fast relative to the speed of light, let's say half the speed of light, this factor would become significant. Otherwise, if we move at a very small speed compared to light, our denominator would basically be equal to 1, and our gamma will be basically equal to 1. So this will account for small speeds and large speeds. But in classical physics, we don't use gamma because the velocities we measure are so insignificant compared to the speed of light. Alright, so this becomes gamma mv over qr. So at this point, you may be wondering, in this problem, nowhere does it mention what r is, and nowhere does it mention what v is. But it does give you the half-life, which is, and because for one full rotation, if it's found that half of the muons decay during each full orbit, which means that one orbit, the length of each orbit is equal to the half-life. The half-life is the amount of time we require for half a sample to decay. So since we're given period, which is the half-life, which is equal to 1.523 microseconds, since we're given this half-life, we can definitely express the velocity in terms of the period. Now, the period is the amount of time you need to complete one full revolution. What is one full revolution? It is 2 pi r. How long does it travel to this entire revolution? That would be the period, which is t. And to travel that distance, you have to multiply it by velocity, right? Remember, vt is equal to distance. So v is therefore equal to 2 pi r over t. So our new equation is gamma m 2 pi, and the r's cancel out, so then we just get 2 pi over q t. So this is our equation for the v field, and let me just label this as the half-life, q t 1 half, t 1 half. Oh, I don't need to write these in, you get the point. We're given a mass, we're given a charge, and we're given a half-life. And for part A, alright, it wants you to find the B field when when the speed is insignificant when compared to the speed of light. Therefore, gamma is basically equal to 1, right? As we have previously discussed. So if you plug all those numbers in, put it in your calculator, you will get 4.85 milliteslas. Alright, so you've answered part A. You've obtained the B field to maintain a circular motion. Now we are looking at part B. And at part B, it says, what if it was moving a lot faster, where gamma becomes significant? Does the fraction of muons which decay during each full orbit increase, decrease, or stay the same? Alright, so this is a little more trivial. If the speed was more significant, gamma would be greater than 1. So what that would indicate, according to looking at these equations, we can see that if gamma was greater, then this orbit would take longer. And we've explained this with our example of the orbiting muon and the observer outside. To the observer, it would look like the orbit took longer because gamma t, gamma times proper time. But the thing is, and it does ask for the fraction. What fraction of muon's decay? Well, if it takes longer to complete a full orbit, it also takes longer. It also takes gamma t longer for these muons to decay. So what does that mean? It means that it stays the same. Even though your orbits are longer, it also takes longer for them to decay by the same factor gamma. And so in the end, what you have is the fraction does not change. Does not change. So you've just completed part A and part B of the A3 problem. And at this point in the video, I'd like to explain how the medal system works for the USAPHO. So to get honorable mention, I believe it's around 1 to 2 problems. More around 1 problem and a few partial correct on the other problems. Bronze, you'll get it around 2 to 3 questions correct. Silver, I'd say it's hanging around 3 to 4. So at this point, you pretty much got a bronze medal. And gold would be a good solid 5 or 4. 4 with some partial credit. Or 5 complete problems. That's a gold medal. But again, this is the 2013 exam. It's a lot, I'd say it's a little bit easier than the previous year. The difference between the two exams is that between F equals MA and USAPHO is that F equals MA is a lot more critical thinking and trivia, where USAPHO just covers a lot more content. So you're going to have to know a lot more. But it's not quite as difficult problem solving critical thinking wise. I mean, all this is really pretty simple once you know the essential concepts. A2 was incredibly easy. A1 was just a lot of knowledge in thermodynamics. Alright, so this pretty much wraps up this video. In my next video, I'll be covering A4 of the 2013 exam. And I will be posting it around tomorrow. I'll follow up with 2 more problems. The B problems are a lot harder than the A problems, so there's no guarantee that I'll get any of the B's in. And I'll see you guys later. Peace.